All right, folks. So we are back, and we're going to be talking today still about PCA, Principal Components Analysis. We're going to be talking about a different way of deriving it, which is kind of known as the minimum error formulation. Now, in the previous section, we derived PCA by finding directions in the data that had the highest variance and the second highest variance, and so on. And for most data sets, which aren't perfectly spherical, that is essentially going to be unique up to flipping of those directions, right? Because the variance along a direction doesn't depend on the sign you apply to that direction. But otherwise, it'll be unique because there will be a direction typically where the variance is maximal, and then there'll be another one which is second best, and so on. So up to that flipping there, that derivation of PCA gives you kind of unique directions. Now, the one we're going to talk about here comes at it from a different perspective, and it comes at it from the perspective, let's say, compression or kind of data approximation. And the solutions that we found before will be one of the solutions to the minimum error formulation, but actually it'll turn out that, and you'll see why kind of geometrically very quickly, why those solutions aren't unique in this formulation. And I think in this chapter, he doesn't actually discuss that. So it kind of comes across as, I'm sure he knows it, but he doesn't discuss it. So it comes across as these two are almost equivalent, but they're actually not. So this minimum error formulation is actually a little bit more general. You can still, it turns out you can still pick the solutions, the PCA solutions we got for maximizing variance, but there is some redundancy. It's kind of a rotational redundancy. And he only discusses this in the problem sets, I think problem 12.2. So I'll just kind of flag that up as we go. Okay, so let's get into it. Okay, so we now discuss an alternative formulation of PCA. And this is kind of where you think, okay, well, maybe this is going to give the same answer. That's kind of the implication. But this one gives a broader set of answers based on projection error minimization. Okay, so what's that going to mean? Let me just give you the picture of it before we get into it. So let me just zoom in so we have a little bit of space. Okay. And we'll first do it in 2D. Okay, so let's say we have a little cloud of points. What we're going to do is we're going to approximate these points, and we're going to say, well, each one of these points, we're going to find a direction in space, and let's call that a different color, so that we can approximate these points as their projection onto this direction plus their mean value along all the remaining directions. So what we'll actually end up doing is approximating the points in this data set as kind of lying along this line, and that line is determined by the mean of the data along that direction. And each of these points is just going to get projected down or up. Right? So the idea will be that, in this simple case, you would say, okay, your nth data point, oh, you can't see that. Oh, yeah, you can. Okay, good. Your nth data point is going to be, approximately, let's call this direction, we'll call this direction U1. So it'll be, xn, this is a projection, plus there's going to be some, constant offset that we'll figure out what it is, times U2. And notice that, this bit has an index n, but this one doesn't. So we're going to find 1b, so one kind of projection along the perpendicular direction that's going to be, we're going to apply to all the data points. And the point is going to be that this can kind of give us a compression, because now we only need to keep one value. There was two values for each data point. Now we keep one value, which is the projection onto this direction, and then there's one overall value, which will be the mean that we're going to apply to every data point. Okay, so that's kind of the idea. Now, this all looks okay and looks a lot like this is going to be exactly like, you can just look at it by eye. Well, if your point cloud kind of looks like this, then, this U1 is going to be the maximum variance direction probably, and U2 is going to be perpendicular to it. So this is exactly like PCA as we derived it in the previous section. But the problem is that, well, the redundancy is apparent when as soon as we go to, let's say we have three-dimensional data. And there you're going to have to kind of bear with my drawing. Let's say we have some kind of a point cloud living there. And now we want to actually, let's make it even easier. So that avoids me having to draw a hyperplane. Let's assume that we have just a point cloud that's actually like it's aligned. Let's say it has one big direction, kind of like a pancake. Okay, so it's got kind of sitting like that, and then and its height is very small. So it's kind of like a pancake. So now in this particular formulation, we want to, let's say, keep the first two principal components. We're going to want to approximate our points by, let's say, by the projections along two directions. So it's clear that if the data really is a pancake, so it kind of, if in profile it kind of looks like this, so it's kind of very narrow in that direction. Well, it's clear that we'd want to project it along the bottom, this bottom surface. But the point is that the directions that we're going to use to do that projection aren't uniquely defined. So we can, I can project the data along this, these two axes, but I can also project them along these two axes, right? Any rotation of those axes will also suffice because you're performing the same projection. You're projecting onto the same surface. So there's kind of a rotational redundancy. So it doesn't make a difference if all you care about is how much you compress the data, but if you actually care about those directions, well, in the previous formulation you would get the directions uniquely. Here you don't. So there are multiple solutions. You can take the old ones, they will work, they will give the correct answer, but there are other possibilities. So you just have to be aware of that. So these two approaches aren't equivalent. Okay, so with that, let's get back into the discussion. So this is good, so you can see till the edge. Okay. Excellent. So let's get on with it. So projection error minimization. So to do this, we introduce a complete orthonormal set of d-dimensional basis vectors that satisfy this. So all this is saying is you were just defining a coordinate axis just like the normal coordinate system. So the normal coordinate system, the one you're most familiar with, it looks like this. U1 is going to be 1, 0, 0, whatever. U2 is going to be 0, 1, 0, so on. And you'll notice that U1 projected on itself is going to be 1, and U1 projected onto U2 is going to be 0, and so on for all the other coordinates, right? So it satisfies this property, but any rotation of that will also, if you think about it, all it means is that these directions have unit length and are perpendicular to each other. So that's what orthonormal means. Well, so we can rotate that whole coordinate system any way we want. Those properties will be preserved. So we are looking for, a coordinate system, not necessarily the default one. Okay, now because this basis is complete, so what does complete mean? Each data point can be represented exactly by a linear combination of the basis vectors. So let's just highlight those points. So here is complete exactly, right? That is what we mean by complete. By linear combination of the basis vectors, right? So here, and we're going to represent each data point as some linear combination of these basis vectors that we chose. And the alpha and I will be different for different data points. Okay, so it's just we're going to project along every direction, in an obvious way. Now this simply corresponds to a rotation of the coordinate system to a new system defined by the UI, and the original D components are replaced by an equivalent alpha and I to alpha n1 to alpha nd. So for each data point, we're going to have D, in most cases, new coefficients. Now taking the inner product with uj and making use of the orthonormality property, we obtain, yeah, so you want to know what these coefficients are? Well, all you have to do, because your coordinate system is orthonormal, you can just take, you can take each of the directions in isolation and project each data point onto each direction, and that gives you the coefficients. So without loss of generality, we can write this. You can write things this way, right? So what are we doing? We're projecting along, each of these basis vectors, and then multiplying by that basis vector, so adding up the components that build a particular data set, a data point. Okay, so our goal, however, is to approximate this data point using a representation involving a restricted number of variables corresponding to a projection onto a lower dimensional subspace. That's what we talked about, right? So we're talking about this projection, that was 2D onto 1D. Then we talked about it doing 3D data onto 2D, so on. And look at the form it's going to take. So the m-dimensional linear subspace can be represented without loss of generality by the first m of the basis vectors, right? So we can just put the ones we care about into the first m slots. And so we approximate each data point by this sum. So that's the bit that's unique to the data point with some coefficients. And notice the n index. So that's going to be potentially different for each data point. Plus this a constant offset that's the same for all the data points. So there's no n index. So no n index. Okay. Where the z and I depend on the particular data point, whereas the bi are constants that are the same for all data points. Okay, so again, kind of going back to our our 2D example. So if we have this is our point cloud, and we have a point here. Well, before we found what the directions are, let's say we decided that our let's make it even I don't know, yeah, that one, say. Well, that's a bit too aligned. So let's say it was like this. Okay, so that's going to be if we pick that as our U1. Okay, so this point here would be let's call it Zn1 U1. So that's the projection of this point. And then the constant offset would be the mean of the data along this direction, right? So if we actually projected, let's put that in a different color. So let's say if we projected all of this data, maybe it kind of looks like, I don't know, maybe kind of looks like this. So the mean is going to be about here, I suppose. So we're going to take this data point, shift it by, by some amount in that direction, and everyone's going to receive the same shift. So the projections, along this direction are going to be different, but everyone is going to be shifted some constant amount along the perpendicular direction. And there could be, of course, many perpendicular directions. So this is going to be a point in the space that you're not using, the kind of the leftover part of the space. Okay. We are free to choose a UI. So you would have seen here that maybe I picked the wrong one. The Z and I, so the coefficients of each data point into that basis, and the BI, so as to minimize the distortion introduced by reduction in dimensionality, right? So that's what we're trying to do, minimize the distortion, reduction in dimensionality, right? We've gone from D dimensions to M less than D plus some offset. So let's highlight this. This is important. To minimize the distortion introduced by, so we want to kind of find a lower dimensional projection plus this offset that minimizes the distortion. Now, how are we going to measure distortion? So as a distortion measure, we will use the squared distance between the original data point and its approximation x of n. So this is something we have to do to get the PCA answer. Using anything else almost always is just much more difficult. So this is kind of one reason why we use the squared deviation. We'll use the squared distance, so let's highlight that. That's important. Between the original data point and its approximation xn tilde. average over the data set. So that our goal is to minimize this thing. So this is important, right? So we're just adding up, this is the squared difference between x of n and its approximation, and then squared, and then averaged over all of our data points. And again, notice that, as long as your approximation is living in a particular subspace, the coordinates that were used to define that subspace don't matter, right? All you care about is the difference. So that's where the redundancy is going to come from. Okay. So now consider, first of all, the minimization with respect to the quantity Zn. So these are the coefficients. So for a given set of ui, we don't know what the good ui's are, but if we did, how would we do that? How would we figure them out? And so this is a good exercise for you to go and figure this out. Setting derivative with respect to z of Zn j to 0 and making use of the orthonormality conditions, we get this. So you can actually go and, you can grind it out, algebraically, figure out what the answer is. But you should also just think of it geometrically, right? So if you have some point and you want to project it onto a space for which you have coordinates in orthonormal coordinates, well, then the projection of that point, the coefficient, is just going to be the projection of your data point onto each one of those coordinates. So you can think about this is kind of a very geometric procedure here. So it's really good to try to build the physical intuition for what's going on, geometric intuition, and then to see how you translate that into math. Okay. Similarly, setting the derivative of j with respect to bi to 0, and again making use of the orthonormality relations, gives us this. And look, right, we can't have an n index, right? It's almost like, well, what else would you be able to do if you weren't allowed to have an n index on this side? Well, you get just the average of the points projected onto the remaining coordinates. So notice what we've done. So we've got, each one of these points has its projection onto all of the coordinates. We're going to keep the projections onto the first m coordinates, and then for the rest, we're going to just use the projection of the mean data point. So we're going to lose information about the individual data points, but if we set up our u's right, maybe that information will be small. So we're going to try to minimize the amount of information that we lose, measured in terms of this distortion. All right. Now, if we substitute for, and let me just make sure that this is important, right? So the j is going to go from m plus 1 to d, whereas the j here is going from 1 to m. So be careful about that. But if you're following the geometric intuition, that should be kind of reasonably clear that that's the case. Okay. So now if we substitute Zni and Bi and make use of the general expansion, which is, yeah, sure, so this one right here. Okay, so we're going to describe, well, you'll just very easily see, right, like what's going to be left? Well, the components of x of n that were captured, that lived in the first m dimensions, we've already captured them, right? So we've already captured them exactly. So all that's going to be left is going to be the components. The only error is going to be coming from the bit that we approximated, and that's what this is saying, right? So it says the amount of distortion you're going to get, this is the averaging, is, notice again, I'm going to highlight this, is that we're going to be, it's just the sum of the projections of the data point along, the m plus 1 and so on dimensions, minus the way we're approximating that data. And if you actually expand this out, it has a very cool equivalent way of writing it, right? So you're just actually projecting each one of these coordinates, each one of these coordinate vectors onto your covariance matrix, which captures, which is kind of capturing the dimensionality of your data. It's capturing all of this x minus x hat, x bar squared, all of that stuff. Okay, so now, yeah, so I mentioned the redundancy. One way, so I've shown you kind of justified it for you geometrically. I just wanted here to justify it for you kind of algebraically as well, so you can see kind of where it comes from. And it's just kind of a fun, fun little exercise. So notice, so I'm going to zoom in again. So let's just make sure you guys were, okay, yeah, all right. So we can actually write this, right? So if we just write this as u, by u, I'll just assume, let's call it, we'll call it u, I don't know, let's say with a little shape like that, to indicate that it's not all of the u, it's kind of the bottom half of the u that we don't care about. Okay, so this is going to be, it's going to have d minus m plus 1 dimensions. So we can write this as well, let me actually just write it for you, in let's have another step. So there's going to be, let's say we have S sitting here, and now let's say we packed U, well, we'll just call it actually what it's called. So U of M plus 1 all the way to U of D. And similarly, we did the same thing, U of M plus 1 transpose all the way. Okay, so now let's call this capital transpose. Okay, so now we can see that this is actually, we've got a matrix multiplication happening, but we're not taking, all of the results. We're just taking the elements along the diagonal, right? Because we just take, whatever the first row times this times the first column. So that's going to be I is equal to M plus 1. Then the second run times this times the second column. That's going to be the second element. And we're going to sum them up. So we can actually write this. So this is just going to equal to the trace of okay. So that's that. Let me erase all this stuff so it doesn't get confusing. Yeah. Okay. So this quantity is, so this thing we have here is the same as this. Okay, so now let's suppose that I'm going to rotate my coordinates, right? So let's say let's say I try the same thing. So I take U, and then I apply a rotation to it so that, U's got all of these columns, and I'm going to apply a rotation. So it's going to combine those columns like with, sines and cosines, basically. I'm going to apply a rotation to it, a rotation matrix, and that's going to be let's call this, let's define n as d minus m plus 1. That's going to be an n by n rotation matrix. And now we'll see that. So first of all, it's clear that that's going to give the same projections, right? That's kind of that's going to give the same x of n tilde or whatever it was. But we can kind of see it here as well. So if we plug that into this expression, we'll get that. So let's just call this v. So then we get trace of. We're going to get this, and now we're going to have u. Forget the v. R, and on the other side, I need a bigger eraser. Yeah, let's just write it over here. Okay, so we're going to get, so let's say u hat goes to u hat r. Then this quantity will go to, trace of r transpose u hat transpose s u r. But trace has a cyclical property, right? So it's going to be the same as the trace of u hat t s u hat r r t, and this is going to be 1, right? Because rotation matrices are their transposes are their inverses, so they're orthonormal. So this is going to get rid of that, and we get this exact same expression. So this is kind of again highlighting that there's rotational redundancy in these coordinates. So if you wanted to see it kind of algebraically, that's one way you could see that as well. It should also be clear, I'm going to zoom back out now. It should also be clear just from the geometric intuition that would hold, but that's another way to see it. So we don't get these coordinates aren't unique. Okay, so let's keep going. The main thing is the intuition that essentially what's left is, the contribution, the difference between the projection of the data in the the m plus 1, kind of the leftover coordinates, and the way we're approximating it. Okay, there remains the task of minimizing j respect to ui, which must be a constrained minimization. Otherwise, we'll obtain the vacuous result ui equals 0, right? Because look, this is going to be a non-negative number because of all the squareds. So if we look at it here, it's very clear. Okay, well, what's the smallest non-negative number? Well, it's going to be 0, right? And we can get that by setting ui to 0. So obviously, we can't have that. Yes, although Another point here is that you can't actually get this result because you have to enforce this, right? So like all the off-diagonal elements, that would be fine, but here this also says that UI transpose UI is equal to 1. So if you, so maybe he's saying the same thing, but effectively you can't just minimize this. We've already we've got some properties on the UIs, right? They have to actually have this orthonormality. So, and I guess maybe that's what he says right after. So the constraints arise from the orthonormality, and as we shall see, the solution will be expressed in terms of the eigenvector expansion of the covariance matrix. Okay, before considering a formal solution, let us try to obtain some intuition about the result by considering the case of a two-dimensional data space. Okay, and I think this is again where the intuition is going to give us the wrong, well, it won't give us the general answer, because in 2 dimensions, the general answer doesn't really show up. You get the same answer as in the previous formulation. It's only when you have some kind of rotational freedom that you actually see, okay, well, these solutions aren't unique. And we actually saw a bit of that. There is a bit of that in the other formulation, right? Like one rotation is just flipping things, to their opposite. So that redundancy is there. But now if you actually increase D to 3 and M is equal to 2, for example, then all of a sudden you're going to have this kind of rotational, this rotational redundancy in the coordinates you choose for your, for your data compression space. Okay. So anyway, but let's stick with this. Okay, I'm just going to say this is misleading example. And a one-dimensional principal subspace. We have to choose the direction U2 so as to minimize this, right? So there's no, U1 is already taken care of. We just have one direction because we're in 2 dimensions. Subject to the normalization constraint, so and so. Okay, so we say, well, what happens? So using a Lagrange multiplier to enforce the constraint. This should be a bit familiar from the last time. We consider the minimization of this, setting the derivative with respect to U. We obtain that S of U2 is lambda 2 U2. So this is kind of it's like eigenvector equation that we got before when we were talking about the minimum variance formulation. Thus, any eigenvector will define a stationary point of the distortion measure. Okay, so but it won't necessarily be the minimum. I mean, to find the value of J at the minimum, so let's kind of highlight that. The one we care about is the one at the minimum. We back substitute the solution for U2 into the distortion measure to give J is going to be lambda 2. Okay, so we're going to get an eigenvector, but we can choose any of the eigenvectors, but we want this thing to be minimum, right? So we therefore obtain the minimum value of J by choosing U2 to be the eigenvector corresponding to the smaller of the 2 eigenvalues. Okay, so we could have chosen either one. This solution, again, is a kind of a thing to notice that you have multiple solutions here, right? You could have picked the principal eigendirection, but then lambda 2 would be large, so your distortions will be living in the space where all the action of the data is. So we want to be aligned with the eigenvector having a larger, so therefore we should choose the principal subspace to be aligned with the eigenvector having a larger eigenvalue, so that what's left is the eigenvector with the smaller eigenvalue, and that's going to be our distortion. So this result accords with our intuition that in order to minimize the average squared projection distance, we should choose the principal component subspace to pass through the mean of the data points and to be aligned with the direction of maximum variance. Exactly. So this is the thing. So I think the redundancy comes from the fact that this method only specifies your principal component subspace. So it kind of tells you what plane you should project your data onto. It doesn't tell you the coordinates for it. I mean, it gives you, you can pick any coordinates for it basically. But this method just picks the principal subspace, whereas the previous method actually picks direction. It says, no, actually the direction with your first principal component is the one with the most variance. We can keep that solution here, as you can see, that is a solution, but we have rotational redundancy here. Okay, for the case when the eigenvalues are equal, which will never happen for real data, any choice of principal direction will give rise to the same value of j. And again, he says a general solution, but again, it's not the general solution, right? So I think he means general because we were considering d equals 2 and m equals 1. Now he says, well, what happens when you let them be arbitrary, as long as m is less than d? And now the idea is, okay, well, what you do is, okay, you say, well, I want, I want the first distortion measure, my first distortion direction to be, maybe the one that has the least power in it, least energy in it, and the second one to be the one that has the second least. So you can just build them up until you run out of dimensions, basically, dimensions that you have left. So it's obtained by, so the general solution is the minimization of j for arbitrary d and arbitrary m is obtained by choosing the ui to be eigenvectors of the covariance matrix given by so and so. And as usual, yep, chosen to be orthonormal. They're going to be orthonormal. So okay, so this is the thing. So they will already. So yeah, because this is S is a positive, let's say positive semi-definite matrix, it's going to have ortho, like its eigenvectors are going to be perpendicular. So you are going to get the orthogonality. The key thing that you won't necessarily get is normality, right? Because if I take any eigenvector and I scale it by some amount 4, well, that'll also be an eigenvector. So the aspect that you would need to enforce is just that these lengths are unit lengths. So I'm going to say that. Only need normality, I guess. I think that's the one. So that's like, ui equals 1, because you get the other one for free. And the corresponding value of the distortion measure is then given by so and so, right? So effectively what we're doing is, another way to look at this is you can, what does S look like? Like suppose that S, and we're going to consider all of its eigenvalues. So it's going to look like, and this is going to be a diagonal matrix that has like lambda 1 all the way to lambda d. Okay, so let's just draw that out again here. So it's going to be u1 to ud, lambda 1 to lambda d, and so on, right? And then this should be, no, that's correct. That's correct. So let's get that back. And this is going to be, and let's move it over a little bit. How far can you guys see? Not too much farther. So, okay, let's just put it there. Okay, and this is going to be U1 transpose all the way to UD transpose. And so essentially this is saying, well, if you want to kind of minimize your distortion, well, you want to make sure that, you want to kind of essentially start from the bottom. So you want to make sure that your first direction, because remember what we're going to be doing is then we're going to be, let's call them, let's go back. So notice what we're going to be doing here. So let's say, because we're free to pick them, I'm going to give them a different letter. So I'm going to call this, let's say V and V transpose. Question is how to pick V, right? So the point is, well, the very first one should try to be exactly this bottom eigenvector, because if it has any other components, so this bottom eigenvector defines the direction, has the least energy in it. If V has any other components in it, then you're going to get a little bit more energy in that direction than you want, than the minimum you could have gotten. So you pick, the first one to be this bottom eigenvector, you get lambda d amount of energy lost, basically. This is the amount that you couldn't, that your approximation loses. Then the next vector has to be kind of proportional, orthogonal to that one, and so you kind of start the process again, but now with lambda d minus 1. And so then you effectively just kind of add them all the way up until you run out of the dimensions that you have left. And so the total energy that you get, the total distortion you get is just a sum of those eigenvalues. Yeah, so which is simply the sum of the eigenvalues. So that's kind of the intuition for it. That's right. And so we therefore obtain the minimum value of j by selecting these eigenvectors to be those having d minus m smallest eigenvalues, and hence the eigenvectors defining the principal subspace. Eigenvectors defining the principal subspace are those corresponding to the m largest eigenvalues. Fine, right? So that's absolutely fine. You can still use, you take your top eigenvectors, and those are the ones that are going to define that principal space. So, and then you have the other ones that define the distortion space, basically. But again, any rotation of those within those spaces is also a solution. So there is that redundancy there, which he doesn't really talk about, except he talks about it in the second. Look at, you can't quite see it. There's exercise. So there's redundancy. It should just be clear from the geometric picture. Look at exercise 12.2. He talks about this, and I might actually solve that exercise in a separate video, so you can see what's going on. Okay. Yeah, so now he says, although we have considered m as less than d, the PCA analysis still holds if m is equal to d, in which case there's no dimensionality reduction, but simply a rotation of the coordinate axes to along with the principal components. And why would you want to do that? Well, we'll see, I think it's in the next chapter, next section, that what this will give you is it will give you uncorrelated coordinates, right? So the idea there is that you essentially find the rotation of your point cloud, and then you project everything along, the axes, the coordinates of that rotation. And when you do that, the resulting point cloud is going to be, aligned with the axes. What does that mean? That means uncorrelated. So there's no trend. It's just sitting, along the axis. All right, and we'll see that I think in the next section. And then finally, it's worth noting that there exists a closely related linear dimensionality reduction technique called canonical correlation analysis, or CCA. So this is a cool one. I haven't had much chance to use it myself, but it's actually very cool. And in some sense, it's kind of a generalization of this, or you can think of PCA as kind of as a special case of CCA. Whereas PCA works with a single random variable, CCA considers two or more variables and tries to find a corresponding pair of linear subspaces that have high cross-correlation so that each component within one is correlated with a single component from the other subspace. Yeah, so you can think about it. I mean, that's one way of thinking about it. So you can think, okay, so I'll just give you a little bit of a taste of kind of what's going on. Let me just, so if you think of this, our S matrix, right? This our covariance, right? It's kind. You can think of it as if we arrange our data in, x1 to xn times, and I'm going to assume that there's no zero mean here just for simplicity, right? And then there is x1 transpose, and then xn transpose. So on, so something like this, right? So we can just write this as x transpose. And now you can think of what we did here. One way to look at it is you can say that, like we saw, so we saw kind of expressions like this. You can think about, okay, so one way of thinking about, what is the first principal direction is to think about it as, finding, you guys can see this, yes, finding u such to maximize, assuming it's, unit vector, u transpose x transpose u. Okay, so that gives you your first principal direction. Now, one way to think about this expression is that you're actually just correlating something with itself. So you're actually saying, you're correlating, let's say it's going to be the correlation, just the overlap of xtu with xtu, right? So you're trying to find these, this u such that to maximize this correlation in unit vector, and it turns out if you do that, then you find the first principal component, and so on. Now, another way you can think about this more generally is you can think, well, I'm actually going to try to maximize this over u and v, right? So they're both going to be orthonormal. They're both going to be unit vectors. So that I'm going to actually maximize. Can you see this? Yes. Maximize the correlation of xtu with xtv. So it's two variables, but kind of working on the same, and it'll give you the same answer. So now the cool thing is, well, in CCA, you kind of just generalize it. So you have, let's say, you have x, and where does this come up? Well, like imagine you have, in neuroscience, we get this, we sometimes get, data sets where, let's say you have two different brain areas responding to the same stimuli. So in one data set, you have, x, which is, number of stim by, n1, and y has the number of stim by n2. So it's kind of, and let me make these, So now what you can do, you can't really, the u's and v's have to be different now, but what you can do is you can still say, look, what I want is, I want to find a u and a v such that, maximize the correlation of xu and yv. Right? So, and you can kind of come up with a basis where, for the two spaces, the same way that the u's were, formed a basis for us of these two spaces, such that you maximize the correlations, sequentially along the basis elements. And so here, this is two data sets, two directions, and PCA is kind of a PCA is kind of a specialization of this, where y equals x, basically, where the two data sets are the same. You're looking for, a direction which has the largest correlation with itself, which is kind of the largest variance, basically. So yeah, but this, I think, just anyway, that was kind of a little teaser about CCA. It's good to know about, because it allows you to compare different data sets, which we often have to do, which can be different sizes, but still has very similar very similar kind of motivation. Good. I think that's all I wanted to talk about in this section. So hopefully you learned some stuff. Please let me know, as always, in the comments. I'm always happy to hear what you like, what you didn't like. And next time we're going to move on to talking about applications of PCA. So it's going to be a fun chapter. You probably already use some of this stuff yourself, but we're going to see what some maybe toy or less toy examples of this look like in the wild, let's say. So I hope to see you there. Bye.